yeah, it feels quite weird that the whole thing happened during lockdown.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System Group at the University of Manchester. You're here with me, Ricky Bahir. We're also here with the usual Dr. John Pernott-Fisher, Tom Harvey.
Hello.
Elliot Carter.
Hello.
And Marissa Lowe.
Hello.
And this is the penultimate episode of the series. So we hope you're all excited. It's just us today, so it's going to be an intimate occasion where you hear about what we've been up to.
Yep.
So feel free to switch off now. John, you've got a paper out.
Yes.
Well, you just had one accepted.
That's right. I've had just a paper accepted 2 weeks ago now in Icarus. There'll be a link in the episode description. So that was exciting. That's mostly what I've been up to over the past, a few months, really. I guess when we started lockdown, I was doing corrections for the paper, and then it went back in, and then I had a few more corrections, and now it's been accepted. So that's always exciting. It's taken a long time, this paper. I'd submitted it, I was looking at it last September. And one of the problems is that it can take forever to get reviews back. It can be very frustrating sometimes, particularly when, your CV needs papers to look better and to advance and to apply for jobs and that. When it takes ages to get papers out, it doesn't really help. It can be quite annoying sometimes. But actually, the paper is about the moon and comets, so it's almost relevant considering there's that comet in the night sky out at the moment. I was looking at noble gas isotopes for the lunar highlands, so all the white stuff that you see in the near side of the moon. And it turns out that using Xenon, you can identify what might be a cometary signature, which is quite exciting. So this is comets that would have been impacted into the moon at some point and imparted that very distinct cometary signature. We've only seen it in a couple of samples, but it's quite good. So this replicates, in a way, data that was produced in another lab. So the fact that we've got two independent laboratories showing this potential signature is good evidence, I think, that this might be a real thing. So it's quite exciting. But understanding comets and stuff is important because it tells us a bit about the sort of impactors that were around in the solar system, and things like comets are important because obviously they're quite water rich, and so if we understand how comets were impacted into the moon, that gives us an insight into how comets impact onto the Earth as well, delivering water and other organic material, I guess.
Is it thought that the impactors of the moon and of other planetary bodies in the inner solar system were predominantly asteroids, but there was a percentage of them were common?
Yeah, that's right. So the exact numbers are still debated within the literature, and that's why it's important to get a handle on what these impactors actually were. And so you can look at different volatile elements like water, like halogens, like chlorine, for instance, being a halogen, to try and get a handle on what sort of the mass balance contributions are of asteroids and comets and stuff. And so it's important to look at a wide range of elements to see what the general picture shows. But most elements, what people think is the case, is that asteroids have predominantly delivered water in some of these signatures. And so the fact that we can see a cometary signature is important because it shows that while there may have been a small percentage of the impact flux in the early solar system, they were still definitely there. But one thing we can't really tell from this data, though, is when this cometary signature was impacted onto the moon. So I guess there are two sort of general scenarios. Either you have comets being delivered recently, so we know that there are constant micrometeorites being delivered to the Earth-Moon system, and so this is effectively what Martin Suttle was talking about a few weeks ago, or a few months ago, where this is the Earth-Moon system, as it travels around the solar system, goes through these debris clouds and debris fields, and sometimes you get a lot of micrometeorite fragments being implanted onto the lunar surface. So it's possible a lot of this stuff has just been slowly accumulating on the lunar surface for however long the rocks I analysed have been sat on the lunar surface, so a few million years. Or the alternative explanation is that comets were impacted onto the moon, but while the lunar crust was still forming, or before it formed, and so it's going straight into a molten moon effectively, and that signature is getting incorporated into the mantle, and then when these rocks crystallize, you're preserving that signature. So it's not entirely clear from the samples that we have which it is. So definitely there were hard measurements to make, and we only see them in, as I said, a couple of samples. So definitely I think there's scope to sort of think about this problem more, and it shows actually the power of xenon isotopes for looking at a wide range of lunar rocks to see if we can see these signatures elsewhere.
So why haven't they been found before?
Well, there's a combination of reasons. So xenon can be quite challenging to measure, and so a lot of historical analyses, error bars have been quite large, and where we're at now with mass spectrometry means that we can measure xenon much more precisely than we could, say, 20 years ago. And a lot of these initial measurements of lunar rocks were made in the 70s, and so there quite wasn't the resolution to really identify some of these signatures. And the other reason, it gets a bit more complicated. And xenon is a tremendously complicated isotopic system. It's got a good number of different isotopes, all affected by different processes. And the cometary signature that I'm going to get into real depth about isotopes now, right? So the cometary signature that we think that we're seeing in these lunar samples comes from two xenon isotopes, 134 and 136. And they are depleted in these samples relative to modern air and solar wind. And we think that that's the cometary signature. Now, 134 xenon and 136 xenon are not stable isotopes. They can be contributed to by, well, they are stable, but they can be added to by fission. And so you get fission of uranium and plutonium that produce these two isotopes. And so in samples like a basalt that have some uranium in them, only a small amount, but say, you know, part per million level is enough to contribute enough 134 and 136 xenon that you don't see this depletion anymore, because you start accumulating so much that it goes off on a trend consistent with fission, rather than looking at these sort of primordial components of the solar system. And the rocks that we were analyzing are really, really low in uranium and plutonium. They've got basically none at all in them. And so you don't get that effect of fission. And so you can effectively preserve some of these original signatures that may have been preserved in these rocks. And so I think that's partially why these things haven't been measured before, or only now that we're starting to sort of potentially see this kind of signature.
What sample were they using in the older study?
Well, some of the same samples, but I think in those cases it was just a case of large error bars, and you didn't quite have the resolution. But because I guess to test this sort of thing, if you had if you wanted to test, for instance, if this was comets being impacted by micrometeorites currently onto the lunar surface, you may want to look at regolith material or soil material to see if you can see that signature. But a lot of those material that we have, because it's just broken up random bits of rock, it can often be actually quite uranium rich in some cases, and so you'd have to be very careful in terms of picking your samples, I think, and try and isolate like uranium poor fragments, I guess.
So you said this paper was quite a long time in the making. When were you originally making these measurements? And is this is the length of time it's taken you to get this all published normal, would you say? For
normal-ish, I suppose. So I guess these measurements did in 2018, maybe. And then I think I started writing the paper September 2018, and that process probably took, I don't know, 6 months. Well, it took till the following September, actually, I guess. So it took about a year to write, and then a further, I guess, number of months for it to be finally published. So
how do you feel about it now?
What do you mean? How do I feel about it?
Do you feel the relief that it's done?
Oh well, yeah. It's always a relief when a paper is accepted. I always get quite anxious when you're there waiting for reviews to come back, because you have no idea if they're going to be good or bad, and you just want to get them and read them. So yeah, and it's always very exciting as well to have a paper published. I guess it's one of the highlights, I would say, of being in academia is actually having stuff published. It's always exciting to see your sort of name in print like that.
You've gone down in eternity now with that, John. In 1,000 years' time, people will be looking at that paper.
Mm-hmm.
Dr. John Burnett Fisher.
The ancient scrolls.
Exactly.
Yeah.
I don't imagine there's many Pernay Fishers about.
No, yeah.
A dime a dozen.
Oh,
Well, congratulations on that, John.
Thank you. Yeah. No, it's interesting. Yeah, comets are quite cool, it turns out. Yeah. Actually, the other thing I should mention about comets as well is that another reason why understanding comets is quite important as well is because we think that it's contributed to the Earth's atmosphere as well. And so we think that the current composition of the Earth's atmosphere is a result of some primordial component being mixed with comets as well. So that's another reason why it's important to understand what the sort of cometary flux was in the early solar system. So yeah.
One thumbs up for comets, eh?
Yeah.
one like for comets.
Yeah. Well, I guess we should throw another congratulations Elliot's way, because Elliot has done his viva for his PhD, and they said you did all right, didn't they?
Yeah.
Yeah, it's all right.
They didn't
Good
say
job.
Get out and stay out.
Yeah.
We weren't in the same room, so they couldn't really say that. So yeah, I had a viva by Zoom, which was quite strange. I've never put on a suit to sit in my own bedroom before.
You put on a suit, did you?
Actually, I didn't wear a jacket, but I did put on a tie and a shirt and
Nice.
shoes.
The shoes part is an odd one, yeah. 'cause
I guess
no
it's
one would
about how you
see.
feel, isn't it?
Yeah,
Yeah.
it felt like it would be a bit strange to like not wear trousers, and then it felt like
Mm. Yeah.
Yeah.
Like into your normal daily routine there, Elliot.
But we'll edit this part out. Right?
So how long did the viva last?
It was 4 hours in the end, and it was crazy because it was 4 hours, but it really didn't feel like we went into that much depth on anything. It was sort of felt like we were skimming the top of it.
Yeah. Well, I suppose that's a testament to what a big volume of work a PhD is, really, isn't it?
Yeah.
I mean, how long was your viva, Ricky, for comparison?
Mine was weirdly quick. Mine's anomalously quick. It was 2.5 hours.
Of course it was. Yeah. Of course it was. Yeah.
Well,
Okay.
it's one of those things where you don't want them to ask questions about things, but at the same time you kind of do. So one of my papers, they just went, "Yep, that was fine," and then went straight on to the next thing.
Mhm.
And I was just kind of like, "Oh, I put hours and hours of my life into doing that."
Ah, yeah, because you did yours by publication. Was yours by publication as well, Elliot?
Yeah.
Okay. Interesting.
Yeah.
And it was still that long. They sound like very long papers. Or was it the introduction and all the appendices and supplementary stuff?
So what was it? It was about 70,000 words in all, I think.
That's a good size. That's a good size. Yeah.
I think one of them was the last one, which I hadn't even tried to submit, was definitely a bit longer than a normal paper.
Mm-hmm. So were you quite nervous about your viva then, or did you feel confident and prepared?
I didn't think it was going to be a disaster, but I was still very nervous anyway. In that kind of way, you can't help be when you care about something, I think.
Mm-hmm.
Mhm.
Yeah, like the few days before, I kept going for like long walks because there's not an awful lot you can do, right?
Mhm.
You can read it and
Yeah.
you can try and think of like what they might ask. But beyond that, you're kind of just waiting.
Yeah.
I prepared a few questions I thought would come up, like
Yeah.
summarize your viva in 5 minutes and
Yeah.
summarize your PhD in 5 minutes, that kind of thing.
Yeah.
Yeah, then I was just like walking around the neighborhood to try and
Mm-hmm. And so what happened at the end? Sorry?
just to keep myself busy. At the end, it was really, they sort of looked at each other and like, okay, well.
Through Zoom, they looked at each other through.
Yeah, sort of. There was an awkward pause.
Yeah.
And then Margaret was like, "Yes, well, you passed."
God, yeah.
And that's it.
They said
Because
it.
in person, you'd normally be asked to leave the room, even if it's a formality,
Mhm.
right?
Yeah.
And you'd go back in and they'd tell you. And I think they were trying to decide whether they'd get me to leave the Zoom room for like a minute
Would you please leave your bedroom?
Yeah.
Oh, but that's good though. I mean, I guess that shows that they'd already largely decided before you even started that you'd passed. Otherwise, they would have still felt the need to deliberate, I guess.
Yeah.
So,
yeah.
how was that feeling then? How did you feel when they said, "Yes, you've now passed"?
I'm not sure I can remember. I guess relief, but mainly just like, okay, that's it.
Mm-hmm.
That was my overwhelming feeling of like the whole thing was like, oh, is that it?
Yeah.
Because like nearly 4 years of your life just funnels down and down into this
Zoom
one
call.
thing. It can never like be as big as all the stuff that you've done to get to that point. So it just sort of feels surely there's got to be something more.
And you were put in a particularly odd situation where you don't even get the relief of handing in like a paper copy of something as well.
Yeah.
You just hand in a PDF and that's it. You know?
Yeah, like the whole thing. Yeah, it feels quite weird that the whole thing happened during lockdown. Like handed it in and viva during lockdown. I think I did the corrections as well before lockdown. I even left it.
So you send it off your corrections now then?
Yeah, I'm totally done.
Nice.
I guess we should explain the process then. So after you've done your viva, your examiners then hand you some corrections and modifications they'd like to see done, which is conditional on you having the final sign-off, I guess, isn't it?
Yeah.
So did they give you many corrections?
There were a couple. It wasn't a huge number, but there were a couple that sort of sounded innocuous on the face of it, and then once I like got into it, were a bit of a nightmare. Not nightmare, just a fair bit of work. It took me maybe 2-3 weeks to do them.
Oh, that's pretty good.
That's not too bad.
That's pretty good.
Yeah, mainly I think because I had 3 weeks between handing in and vivaing, which was really short. Partly because with Zoom you don't need to like get everyone in the same room, so there's no like scheduling issues so much. So like they just read it and then did the viva, and then 3 or 4 weeks later I handed in. So it was all very condensed. I think I never like emotionally got past like handing in. I was like a stress level, and I never got down. So like going back to do the corrections, I really didn't enjoy it. I was like, no, I'm emotionally done with this. I closed the book on it. I don't want to look at it again. So I didn't enjoy that.
But that's the standard thing in academia, really. A lot of things you finish the same task multiple times.
Yeah.
Like with a paper, you send off a paper and you kind of get that feeling of this is done. You know, I've done it now. But then you get the reviewer comments back, and then you do those, and then you send it back off again. And then they say, okay, great. Can you now change this little thing? So by the time you actually finalized it for the final time, you've done it 3 or 4 times.
Yeah, absolutely. The whole thing's felt like just really raggedy end. There's no like moment of closure. Because I'm still working on the papers that were in my PhD. I'm like, doing revisions on them. So I don't think I'll ever see the back of it.
So particularly at the start of doing a PhD, one thing I heard a lot was by the end of your PhD, you'll be the expert on the topic. So Elliot, do you feel like the expert? We're asking you all the deep, profound questions.
Right. No, I mean, I think I have pretty major imposter syndrome most of the time.
Well, everybody does, though. That's perfectly normal.
Yeah. I don't know. I guess I know a fair bit about halogens and ophiolites compared to a normal human being.
Yeah.
I mean, for lots of people, myself included, you'd have to be like, what are halogens, what are ophiolites?
Well,
7 in the periodic table.
I think we've just unlocked the ability to have like cards signposted in. So if you're watching on YouTube, we'll put a card to your episode, Elliot, in this corner.
Cool.
So the listeners can find out a bit more about halogens and ophiolites. How about that for a plug?
Of technology.
Yeah. How about that?
That's your weekend sorted for you listeners.
That's right.
Once you go down the halogens and ophiolites rabbit hole, you never come back up.
Oh my god, yeah, it's a sweet drug.
Which is ironic because I guess most halogens are by definition quite salty.
Yeah. Good.
Oh. It is far too warm to be making jokes like that.
So Marissa, you've taken time out at the moment from your PhD to explore some other research areas.
Indeed. So I'm still looking at the moon, but I'm actually looking at a mission planning project, which, as lots of you will know, is very different to what I normally do, which is lots of numerical modeling and image analysis. So yeah, mission planning and doing something more practical is very different to my normal PhD work. So it's part of the ESA Lunar Caves project, which was a general call for mission proposals, I think last year or the year before, and there's about 5 or 6 different universities that submitted proposals that are now through to the second round. So I'm working with some people from the engineering department here in Manchester, and then Katie Joy, my supervisor, and someone who we've had as a guest on here a couple of times, on planning a rover mission to a lunar lava tube. So for context, lava tubes are, how do I say it other than a tube of rock? If you imagine a lava flow, this molten lava flow, it's going to cool from the outside and from the top first. So eventually you build up a crust that kind of thickens, leaving a flowing molten core within it. It's basically just like a pipe of lava. So these things are mostly found at basaltic volcanoes. So you see them in Iceland, Hawaii. I've been inside one in Etna in Sicily, which was very fun. Maybe I'll insert a picture here. And they're generally tens of meters long, maybe hundreds of meters, a few meters tall, or they can be just a few centimeters in size as well. And yeah, they've gotten some publicity, I suppose, for being heralded as a possible habitat for if humans are going to go colonize the moon. What are we going to use as protection from radiation and micrometeorite and meteorite bombardment? So lots of people have said, well, these lunar lava tubes could just be natural caves for humans to live in. So the one we're looking at is in the Marius Hills region of the moon, which is a very, I think it's the most densely populated area in terms of volcanic domes. I think there's over 200 domes and cones that have been identified in the Marius Hills region. So
sorry, I assume they're viewed from satellite images. People have seen these domes, on the surface.
Yeah. So just, yeah. So about 10 years ago, using the Kaguya camera, so the Japanese lunar orbiter, which I think has been in orbit since 2007, they identified a lunar lava tube skylight. So this is basically where that nice solidified crust has collapsed in a little bit. So again, we see this on Earth, and they identified it using these images as just a pretty circular, deep well, I suppose. It's about 80 meters across, so quite big if you were to imagine standing near it.
Do we have a sense of the depth of these things?
It's quite hard to estimate, so I suppose that's part of the reason why ESA put out this call for how would we start exploring these lunar lava tubes before we start sending people down there. How deep are they, and what are the conditions like in there? So as I said, I've kind of joined this project midway through. I think it's been in the works for a couple of years now, but they were keen to get someone on who knew more about the lunar science side of things. So the engineers have all been working on this hopping rover. So quite hard to describe without any pictures or anything, but it's sort of like a wire frame, vaguely spherical in shape. And when I say bio-inspired and hopping, it's because it's making use of, I guess, the physics of people jumping. I'm not sure. What it does is it compresses down, this wire sphere compresses down, and then uses that some elastic energy from springs inside the rover to hop and propel itself forward. So I've only seen some videos of this. I think they've made a few prototypes in the labs here in Manchester. But yeah, it's quite small, like the size of a loaf of bread. And my task has been deciding what instruments would we want to put on this. So what would the payload be? And more importantly, what science questions can we answer from that? So yeah, as I'm sure you all know, there's loads of things we wouldn't know about a cave on the surface of the moon. You know, what temperature is it? What's the radiation like in there? What do they actually look like? Are they really hazardous? Are there going to be loads of things falling down? Yeah, what size are they? What can it tell us about heat flow on the moon? Yeah, lots of things that we don't know that we could answer by exploring these caves.
That's really cool. So what you're saying then, basically, if I understood this correctly, you got this hopping thing that's going to hop into a cave, do its measurements, and then hop back out again.
Yeah, so I think the idea would be that it would have a little explore of it, maybe create some sort of map while it's in there, and then
that's really cool.
Engineers work out how to get back out.
Yeah. Because how high could this thing hop then potentially in terms of the size that this mission's being planned for?
I think a few meters, but we're going to think about scaling it to different sizes.
That's awesome.
Would you communicate from inside the cave, or is it like totally blind once it goes in?
Yeah, I think it would be probably, we'd have to stick lots of data storage things on the rover so that
couple of USB sticks.
Yeah, exactly.
So I don't know a great deal about these lava tubes. And where does the magma actually come from that forms the tube itself? So the reason I'm asking, could it be a case where when you get into the tube, there's just a massive hole in the ground that the thing could fall through? Or does it not work like that?
Yeah, so I guess your first question, where does it come from? So these erupted onto the surface. Yeah. It's within a lava flow. So if you just imagine a vent at the surface of the moon,
right? Okay,
it's poured on to the surface like that. And yeah, you're absolutely right that there could just be a massive hole when we drop in there because these lava tubes can actually be interconnected. So I don't know how often you guys watch videos of lava flows, but big hobby of mine.
Daily.
But if you imagine a lobe of lava, it's solidified a bit on the top to form a crust, but there's still lots of lava being pumped into that lobe. So pressure builds up in there and it bursts out, forming another lobe. That's basically what's happening here, but within the tubes. So sometimes, as I said, you can get roof collapses in these lava tubes that can block the tube. Pressure builds up and that's got to go somewhere. So another tube can form off the side of another one. So yeah, if you imagine like a rabbit warren, how they're all interconnected tunnels, that's what the insides of these lava tubes could be like.
So you're saying the lava is sentient and it knows what it's doing when it makes it? Yes, okay. Good. I understand. I fully understand now.
Yeah, I guess it's interesting. So, but really, our main unknown then is how deep these things are, and I suppose like lunar magmas are quite diffuse, aren't they? They spread out quite thinly. So I suppose that gives us a first order impression then of how thick we might expect these things to be. I don't know.
Yeah, and there's been obviously a lot of studies about terrestrial lava tubes and thinking about what combination of wall thickness, height and width, stability-wise actually works. So we've got some idea of what ratio we'd at least find the size of these in. But yeah, it's been a very fun project to work on so far, deep diving into lots of old missions and thinking about what instruments they've been using. Something I've been looking at a lot is LiDAR, so light detection and ranging. So this basically would be our little tool for mapping the inside of the lava tube. So this would be something on the rover shoots out a laser. That laser goes out, bounces off a wall and comes back into a detector. And based on the amount of time it takes for that laser to go back and forth, you can work out how far away your lava tube roof is or something like that. So most of the things I've been looking at have been for cars and things like that, and emailing lots of companies to go, hi, what temperature can I use your LiDAR system at? I need it to be at -80 or something, and then cope with a temperature increase of this much in 5 hours. Can I do that? or will it melt?
And do a lot of them say, "Oh, we just tested this actually"? So it's good.
It's interesting. We actually just tested this in a lava tube on the moon. So it's
Sadly not. Sadly not.
So where do you even start then? So by the sounds of it, then you've got a pretty much a free reign to try and figure out what your payloads should be. That seems to me to be quite. I think I'd be quite overwhelmed then in terms of choice. Like how have you narrowed down what kind of instruments you want to put on and what sort of questions you want to address?
So, I mean, as Tim Gregory said last week, all good things start with an Excel spreadsheet.
Yeah.
It was just kind of that, starting with that and a list of science questions, splitting them into, right, human habitation. What are the main things that we'd want to know about that if we're going to send humans to go live in these? And then it's also mostly what me and Katie enjoyed, thinking about the geology and the volcanic history of the moon. Size has been a massive funnel filter for deciding what instruments to use.
Yeah.
As I said, the hopping rover, it's only about the size of a loaf of bread and would probably only be operational with a payload of around 1 kilogram or so. So that's,
oh wow,
yeah. And so to find instruments that would be suitable for that, I've been looking at CubeSats quite a bit. So these are very small, like I think they're only up, I think tens of centimeters cube-sized satellites. So that's been really good for finding small scale instruments that are still durable and can last okay in space.
Yeah, and then presumably in all that you've got to fit some power as well.
Yeah. So I actually don't know much about that side of the project. I've left that kind of to the engineers. But it's been fun working with them to see all the different cool things that they can do. So as I said, temperature is going to be pretty important. I mean, we know even what phones are like. If it gets too cold, the batteries can just drain instantly. So it'd be awful to think in years' time if we sent a rover up there and then it just completely discharged within seconds of going into a lunar lava tube.
So what would the process by that this could eventually become a real mission be?
So as I said, we're in the second round of planning for this, and there's I think 5 or 6 universities that have been selected, and their proposals have been selected. And I think in December, ESA are going to get everyone together again and review all of the projects. I think it's going to be, from what I know, a bit of a Frankenstein. So a bit of a, okay, we're going to take bits from that project and bits from that project. And then, from what I know, the next time there's a big pot of money, this could be put forward as a proper mission proposal.
And when they're like the people who came up with those ideas, would they get to be involved just, or are you like doing this as a bit of work and then it might have nothing to do with you in the future?
I think, you would continue to be involved, and also, especially for things like making the rover, the prototypes and all that. I think the people who put the proposal together would still be involved.
That's really cool.
It's really exciting to get involved in an actual mission that could occur. That's crazy. Yeah,
definitely. But it has definitely made me appreciate how long it takes for these missions to be planned. And obviously we've spoken to quite a few guests over the series about missions being pushed back, and that it's like James Webb Space Telescope. It's crazy to think that something that has been planned since say 2018 for this Lunar Caves project probably wouldn't happen for another 5 to 10 years at least if everything goes.
Well, I guess a lot of money go into these projects, so there's a lot riding on it being exactly what you want it to be, and making sure it all goes exactly to plan as well. Because as you said, that small thing, like say you just got the temperatures wrong and then your battery drains immediately as soon as you get there, you've wasted so much time and so much money on something. So it has to be made. You just got to make sure it's exactly correct, really.
So how long are you working on this project for?
So I started working on the project start of July, and we'll be finishing up with it at the end of this month. So going back to PhD work from the start of August, which should be fun. But I think even after I finish this sort of 2-month internship, I'll still be contributing to the project.
Yeah.
Well, it's incredible that you've got yourself involved in such a great project, Marissa. And again, well done to you, Elliot. Congratulations. And on a lesser note, congratulations to you, John, as well. But it's good to see you got that paper out finally.
Yeah.
So we should just say thank you, everyone, for listening
Mm-hmm.
to this penultimate episode of the series. The final episode will be out next Wednesday.
Yes, so we've got something a bit different planned for next week, so keep an eye out for that on Twitter for when we release our next episode next week. But in the meantime, thank you all very much for listening. If you want some more Earth and Solar System content, of course, as per usual, we're all over social media, from Twitter to Facebook to Instagram. Find us everywhere at Earth Solar System. Links will be in the episode description. But until then, see you all very soon, and goodbye.
Bye.